Since the boom of generative AI, people cannot stop talking about data. But what happens if you don't have enough real-world data to actually feed and train these large language models? Well, in comes synthetic data. My name is Corey Hughes and it's time to decode it. So when it comes to synthetic data, people often have a couple of questions. And the first one is, well, what is it to begin with? So synthetic data is basically just artificially generated data that's whole purpose is to basically mimic the patterns and distributions in the real world data. And the second one is, even if you can obtain the data, it's actually quite costly to store it, to manage it, to process it, to clean it. And then sometimes it's actually not even there to begin with. So in cases like rare diseases, there's very limited availability. And this was something I found very interesting in my research, because what they'll do in healthcare is they'll take real world data and they'll take synthetic data and they'll merge them together so that there's enough data there to train a large language model. And the third question that people ask, and my favorite, is how do we even create synthetic data? So there's a couple of ways that you can do it, but in this video, we're going to be focusing on GANs, which stands for Generative Adversarial Networks. And they've been around for about 11 years now. They were created in 2014 by Ian Goodfellow, and we started with what's called a traditional GAN. So a traditional GAN has a generator and a discriminator. And the discriminator is fed with lots and lots and lots of real-world data until the discriminator can say, do you know what, I'm confident I know what real-world data looks like. The generator is then fed with just noise, and that noise is generated into synthetic data. The generator then takes that synthetic data, gives it to the discriminator, and the discriminator, using binary cross entropy, will decide whether it's real or it's fake, hence the binary. It's either 1 or it's 0. And then we use a sigmoid function to basically squeeze that output, that result, into either a 0 or a 1. It is or it isn't. Now, that's our traditional GAN. As the years went on, GANs got more advanced, and we have something called a WGAN-GP. Now, a WGAN-GP stands for a Wasserstein GAN with a gradient penalty. And the difference between this and a traditional GAN is that a WGAN-GP has a critic instead of a discriminator. So the critic is just more informed, okay? Because what it does is the critic uses a Wasserstein loss or an Earth mover's distance to basically tell the synthetic data how far away it is from the real data. So it doesn't just say it is or it isn't. It says you're about 70% of the way there. And the magic behind the critic is that we have the gradient penalty too. And the gradient penalty basically tells the synthetic data what it needs to improve on in order to be more like the real data. So you can see the difference here. Traditional GAN, binary cross entropy, 0, 1. WGAN-GP, critic, Wasserstein loss, gradient penalty, it's more advanced. Now, at a high level, it looks like this. The noise goes into the generator. The generator creates the synthetic data. The synthetic data is then put through to the critic. And what's cool about WGAN-GP is that the critic then outbounds an unbounded number. So it doesn't just output a 0 or a 1. It actually outputs a real number. In this case, let's say it's a 7. So we'll take that 7 and we'll compare it against a predefined threshold number given to the real data. So in this case, let's say the real data is given a 10, our synthetic data is given a 7, our Wasserstein loss is a 3, that's fed back through into the neural network and outbounded until we get a result that we're happy with. Now, there's obviously a WGAN and there's a WGAN-GP. What's the difference? It's just the Lipschitz constraint that's enforced. And the Lipschitz constraint is basically just how we smooth the gradients. So with a WGAN, it uses weight clipping. The WGAN-GP obviously uses a gradient penalty. Gradient penalty is just more stable and leads to less mode collapse. So if we look at them all together, our GAN, our WGAN, and our WGAN-GP, keeping in mind that this is just 3 GANs. There's C GANs, there's V GANs, there's so many different types of GANs. But the 3 ones that we focused on here was our GAN, which is binary cross entropy, so it outputs a 1 or a 0. It doesn't have any Lipschitz constraint and it's actually quite unstable. Then we move on to our WGAN that has a real number outputted. It uses a Wasserstein loss, so an Earth mover's distance, as its loss function. It uses weight clipping as its Lipschitz constraint, and it's better when it comes to mode stability. And then our WGAN-GP is the same as a WGAN, but it uses a gradient penalty as its Lipschitz constraint. So as this series continues, we're not only going to be talking about GANs, we're actually going to be implementing our very own GAN using Python programming. And we're going to be using those results and those samples and comparing them against each other for predictive analysis with linear regression to see who outperforms who, the synthetic data or the real data. If that's something you're interested in, hit subscribe and I'll see you in the next video.